Hello, welcome back to Math 332 Linear Algebra. This is a video on Chapter 4, Section 4.1, where we're going to study a concept called vector spaces. And this is a very important topic in linear algebra, and this is also a topic that students usually find very difficult in the beginning, so I want you to pay attention to it. Actually, the things that we're going to study today is actually not very complicated. Is basically what we want to do is to look at vectors, the vectors that you're familiar with. You probably first encounter it in physics, in high school physics. So we look at the usual vectors that we know, together with these operations, which is additions and scalar multiplications. We realize that vectors, together with those two operations, satisfy a list of property, which basically define what vector is. And by looking at other mathematical systems, we realize that for a lot of mathematical systems, they also exhibit the same type of behavior. They have the same property as our usual vectors. So we are going to use this concept called vector space to basically lump all of them together, put all of them together under the same umbrella, so that when we develop a theory, we just need to develop a theory for one thing. That thing will works for the usual vectors, will also works for other type of mathematical object that share the same properties as the usual vectors that we know. And that's basically the concept of vector spaces. So at the end of this video, you will see that we can actually call a polynomial as a vector. We can also call a function as a vector. We can call a matrix as a vector because under the settings that we're going to discuss, and we'll look at the details, that those objects are basically vectors because they behave as if they are like the usual vectors that we know. All right, so in order to understand well the concept that we're going to lay out today, you just have to pay attention to the definitions of vector spaces, and we're going to look at many examples so that you will get comfortable with this new concept and new idea. Okay. All right, so let's begin by looking at the objective for this section. So at the end of this video, you should know what is a vector space, and given a set together with the additions and scalar multiplications, you should be able to determine whether that set together with that two operations actually form a vector space or not. Okay, so let's start from very beginning. That is, what is a vector? So you probably have seen it before. Maybe the first time you encountered it was in physics, but you also have seen vectors before in calculus, in Calc 3, multivariable calculus, so on and so forth. So you know that a vector is a mathematical object that has magnitudes and directions. And the way we write them, there are many different notations. You probably see vectors written like this, vector written like this, and in printed books sometimes they just simply bold that vector, so you have something that's like this. But I would not use this notation because it's very difficult to write. But in your notes and in your homework and exam and stuff like that, you will see a bolded notation that is used to represent vectors. So let's look at a very simple example and say you have a vector that is like this. You can see vectors being written as a column matrix. This is known as a column vectors. You will also see vectors is written like a column as a row matrix, which is like this. This is the row notations. And for example, if you are in calculus, you've probably seen a lot of notations written like this. And this is simply because it's safe space, you know. So it's printed space is precious. So sometimes you will see books usually tends to use notation like this for calculus and stuff like that, but they are the same thing. These are the vectors that we are saying this in Euclidean space R2. We'll talk more about that later. And I'm pretty sure that you know how to look at the representation of vectors. So this is a vector in R2. You can actually put them in a coordinate system. And so this simply means 1 in the x direction and 2 in the y directions, and you can compute the magnitudes pretty easily. So this is the vector u, which is starting from here and ending from here. So you can see there's the directions right here. So this is 1 unit here, 2 unit here. So the directions, you can compute that. Tangent theta is going to be 2 over 1. So you can compute the theta to indicate what's the directions of the vectors that is pointing at, and also the magnitudes. You can use the Pythagorean theorem to pretty easily compute that the notation for the magnitude is something that looks like this. And you will see that this is nothing but 1 squared plus 2 squared, which is square root of 5. So this is a very basic review of what is a vector. So this is square root of 5. So we have a magnitude, we have a directions, and there's another way of indicating the direction of the vectors, which is using so-called the unit vectors, which is basically takes your vectors divided by this magnitude. So this is purely used to indicate the directions. Because this is always magnitude 1, and then if you have something that is like 2 times the magnitude in that direction, you just simply multiply 2 to these vectors. So we'll come back to this at the end of the semesters, where we are going to talk about how to construct projection vectors, stuff like that. So I hope that you will remember all this basic stuff, and I will remind you from time to time. Okay, so all these vectors are the fixed vectors. It's always just 1, 2. It won't change. Just 1, 2, and you can move them. You know that these vectors, all these vectors that's pointing in that direction with the same magnitude, they are all equivalent vectors. So you can move them, and you can add them, you can scalar multiply them. And so this is a very quick and basic review of what vector is. All right, vector can also be non-statics. For example, if you want to represent the flow of a particle of a fluid past a propeller, and you can see we can also indicate all that through the use of vectors. But now your vectors will be actually a function of time, so this will be something that looks like this. Just for example, I didn't mean that this kind of vectors is written exactly like this, but I'm trying to show you a type of vectors that depends on the input right here, and you will see stuff like that in your multivariable calculus. So this is one vectors, but this is going to be a vectors, infinitely many of them, which depends on the variable t, which usually stands for time. Okay, so this is the type of vectors that we know that is from R2, and this is the type of vectors that we said is in R3. So you probably can guess in general in Rn is what we call a Euclidean space. It is a set that consists of elements that looks like this. So the elements is the n by 1 column vectors. And also you probably haven't seen kind of sets notation like this before. So this is what we call a sets builder notation. So this is what we call a sets builder notations. And what it says, okay, the way we do it is to first write down the elements and then provide the descriptions of the elements. So you can write things right here to say more about this this particular elements here. And you can either use a vertical line or a double dot right here. So for example, you can say is that I have a set called P, and this is a set consists of let's say okay, let's say we have P. Okay, let's say it consists of elements as of the form A, B, where A, B here is integers, and then B here is not equal to 0. Okay, so this is actually what we usually known as the sets of rational numbers. So you can see that we try to indicate how the elements looks like, and then we provide descriptions for these particular elements right here. So there are two different ways of writing down the elements of a set. You can list down all the elements, but sometimes that's not possible to list down all the elements. So we use sets builder notation. So you can see this is what they're trying to tell you. The sets Rn consists of elements that's like this, and then they are trying to explain what are all the x1, x2, all the way to xn, and those are real values. So these are real numbers. That's the reason why you have R right here. And you can also probably know and guess that if you are putting complex number here, then the thing will be a set that is like this. Okay, so we don't study complex number. We don't use complex numbers in this course right now. But in physics, if you're a physics major, when you talk about your vector spaces and we talk about your linear algebra, you use physics. In a lot of situations, you will see complex numbers, but unfortunately, we will not be able to talk about it in this course. But just to let you know, instead of Rn, you also have Cn, okay? Okay, so what is Euclidean space? So Euclidean space is not just a set consists of all these elements. These are all the vectors. So we can actually also define two different type of operations on it. So this is basically a vectors. So we know we can add them, so they are of the same size, well, we can add them. So this is called vector additions, and this is actually how we add vectors in physics and so on and so forth. So this, when you add this two vectors, you add up all the correspondence components together. So this is not a big surprise. We've seen it before. And this is what we call scalar multiplications, where you take numbers, in our case, real numbers, and multiply it with vectors. And the way you multiply is you multiply every single component with that number c, okay? So this is how we multiply a scalar with a vectors. We haven't talked about other types of multiplications. There are dot product, which we will talk about at the end of the course, and there's also cross products, which you will talk about in Calc 3. But we won't talk about that. So for linear algebra, the only type of multiplications right now that we care about is the scalar multiplications, and this is what we call the vector addition. So this actually translates to, let's say in R2, you have a vector that's u, and then you have another vector that is v. Okay, so the way you add vectors in physics is that you translate that u is still here, but you can move v because, as I said, these are equivalence vectors. They are still having the same magnitude and still pointing in the same directions. So instead of this v, okay, we can move them over here. And then think about if you start from here, right? And then you walk to here, and then you walk to here. So the shortest distance is here. So this is a u plus v. I just want you to know this notion is completely equivalent to this. So if you have u as u1, u2, and then if you have v here is your v1, v2, the vectors u plus v is actually given by the sum u1 plus v1, u2 plus v2. All right, so this is all the vector stuff that you should know from your previous encounter with vectors, either from physics, engineering, your calculus, and so on and so forth. So in the study of vectors, we realize that vectors, okay, together with the additions and scalar multiplications, satisfies these 10 properties, okay? So you take two vectors, u plus v. If your vectors u is in Rn, your vectors v is also in Rn, adding these two vectors will still be in Rn. This is what we call closure under additions. So this is also trivial. If you have a vector u that is in Rn and you scalar multiply that vectors with a number, it is still an element that is in Rn. As you can see, this thing right here and also this things right here, they are still elements in Rn. Nothing really changed. So this is called closure under scalar multiplication and closure under additions. And vectors additions are commutative. So u plus v and v plus u is the same. This is called the associative property. So vectors additions have this associative properties, which means that whether you do this operation first or you do this operation first, it doesn't really matter. You will get the same vectors. So this is the things that we notice for vectors addition and scalar multiplications. And also there's like a 0. There's a vector 0 in Rn. So this is a vector 0, which is actually something that looks like this. Okay, this is called a 0 vector, such that u plus this will equals to u. There's not only a 0, there's for every element, there's also a negative. So for a vector u in Rn, there's a negative u in Rn, such that the sum will give you the 0 vectors. So this is all the properties for vectors involving additions. And these are all the vectors, properties for vectors involving scalar multiplication. So you scalar multiply c with u plus v, you can kind of like distribute. So this is not a big mystery because we know how matrix operation works, and all these vectors are basically matrices. So this is also not a big surprise. We also have this distributive property, and we also have this distributive property, and we have a number 1. The number 1 here times that vector u's will also equals to u. So these are all the property for vectors that is in Rn. So by studying the Euclidean space, not only just R2 and R3, but in Rn, we realize that vectors addition and scalar multiplications, if you think about it, they all just basically satisfying all these 10 basic properties. So all the properties for vectors addition and scalar multiplication can be summarized up to these 10 properties. So it's kind of like if you think about how you could summarize what is the things that best describes you, and come up with, like, say 10 different things, and that 10 different things defines you, right? So for example, you are good looking, tall, smart, have a lot of money, and I don't know, like, just for example, like things that defines you, like you like to play computer games, or you like to play basketball, or you like to play tennis, or something. I don't know, like, just come up with a list, maybe more than 10 items, but they will be a list that kind of like properly define you. We kind of like doing the same thing for vectors, addition, and scalar multiplications in Euclidean space. So we look at it very thoroughly and realize that they can be completely summarized by these 10 properties. Okay, so now I'm going to give you a definition of a vector space. Okay, so we're ready for that now. So if you have a set, okay, with two operations defined on it, it's called addition and scalar multiplications. And then, okay, so if this u and v is in this set v, the sum of u plus v written like this. Okay, and if you have a scalar c, the scalar multiplications is written like this. These are just introducing you the notations. And so if you have a set with two operations called addition and scalar multiplication, these are the notations. And if the addition and scalar multiplication satisfy this 10 axiom, then we'll call that set. Okay, we'll call that set. Okay, together with the additions and scalar multiplications. This is like kind of the stuff that I can use for notations. So this right here is going to be known as a vector space. Sometimes you'll see people write this. This is a notation to indicate that we have a set, and then we have two different operations defined on it, the addition operation and scalar multiplications. Then this new objects here will be known as a vector space. So vector space, by definitions, is a set. Okay, so it's a set together with two operations. And those two operations are known as addition operations and scalar multiplications. These are how we write additions and scalar multiplications. And if with the addition and scalar multiplications, there's they satisfy this 10th axiom, then the set together with these two operations is known as a vector space. And not only that, every element inside this set is going to call a vectors. Okay, it's going to call a vectors. Now, the whole story for this section is this. Okay, the whole story for this section is this. We study a lot of different things in mathematics, and we actually realize that not only Rn has this property, a lot of things actually does have this property. So instead of creating many different theories for many different things that we study, we found that they all fit into this framework. Everything fits into this framework. So we want to take an abstraction. So we want to say that, hey, all these things are actually the same, all right? They are kind of like a vectors. When we say vectors, the things that we are familiar with, these are the vectors that we are familiar with, right? So we look at a lot of things, which we're going to give you some example today, that they all behave as if they are like a vectors in Euclidean space. They are just like the vectors we study in physics. So instead of study them all separately, we make a definitions, which is this. We list down all the things a vector should have, and then if you satisfy this kind of 10 axiom, you will qualify yourself as a vector, and you basically behave like the Euclidean space, the normal usual vectors that we study. Okay, even though Euclid looks very different, but we will still call you vectors because we are kind of like the same family. Okay, so let me give you some example. Okay, so for example, let's look at this set right here. Okay, all right. So now we have this set P2. So what is P2? P2 is a set of polynomial of degree at most 2. Okay, so if you want to use sets builder notations, we can write this is like A0 plus A1x plus A2x squared, right? So these are how the elements looks like, where A0, A1, okay, A2, these are real number, okay? So this is a polynomial of degree at most 2. So what is in P2? So things that's in P2 could be 1 plus x. This is in P2 because this is a polynomial of degree 1, right? The highest power here is 1. So this is a polynomial of degree at most 2, right? So you can also have this polynomial. So this is polynomial px equals to 1. This is not a number. This is a polynomial px equals to 1. You can graph it, right? So you know from calculus, this is what we call the constant value functions. So this is also in P2. So you can write like that. This is an element in P2. This is an element in P2. All right, so x squared is also a polynomial of degree at most 2. So this is in P2. 1 plus x squared, this is also in P2. However, 1 plus x cubed is not in P2. So this is not an element in P2, right? So P2 is a set. Okay, so right now P2 is just a set. It's a set of polynomial of degree at most 2. Okay, all right, now. So we haven't talked about vector spaces yet because a vector space would have to be a set together with 2 operations. So in order to be able to talk about vector spaces, we not only have to look at the set, we also have to talk about the additions and scalar multiplication operations. So we define additions as the usual polynomial additions. This is actually how you add polynomials. So if you have a polynomial of degree at most 2, you call it px. You have a polynomial of degree at most 2, you call it qx. Px plus Qx is written like this. So the way you do it is to look at the corresponding entry. This is called the constant terms. So you add up the constant terms, okay? And then you add up the coefficient for the x, okay? And then you add up the coefficient for the x squared. So this is how you add polynomial. And this is actually the usual way we add polynomial, okay? And how do we scalar multiply a polynomial? How do you take a polynomial and multiply with a constant? Well, you multiply every corresponding entries here with that c. So this is actually how you multiply a polynomial with a scalar. Okay, so now the key thing is, once you have a polynomial, okay, of degree at most 2 with this kind of addition and scalar multiplication, you can go through this 10 axiom and you will see that, okay, all this 10 axiom is satisfied. If you have a 2 polynomial of degree at most 2, you add it up, it's still a polynomial of degree at most 2. Polynomial additions is commutative. Polynomial additions is also associative. For every polynomial, you have a 0 polynomial that serves as a 0 vector, such that a polynomial plus a 0 polynomial will equal to that polynomial, and so on and so forth. So in your notes, you actually will see that I actually go through all very detailed computations to actually show you that P2 is satisfying all this 10 axioms. So we have a notes, we go through all this in detail that shows you that all that 10 axioms is satisfied with polynomial of degree at most 2 with these 2 additions, operation, and scalar multiplications defined like this, which means by this definitions, okay, so which means by this definitions, this set right here, together with these 2 operations is basically like the vectors that we know in R2, in R3. They are basically the same thing because they basically satisfy everything that define how do you have to be in order to be in called vectors in R2 and R3 and in general Rn. So polynomial of degree at most 2 actually does satisfy all those properties. So they are basically essentially behave like the typical vectors in R2, in R3, and in general in Rn. So we were going to call this sets right here. So I'm going to write this right here. So we are going to call this P2. And then we want to indicate that not only just the set, we also talk about the additions and scalar multiplications. So this right here is actually a vector space. It's a vector space, okay? For simplicity, most of the time, people just drop this addition and scalar multiplications and just write P2. But you can also see books that indicate vector space like that to kind of like display that prominently, actually, that we not only talk about the sets, we also talk about the operation. But for simplicity, you can also see that a lot of books just write P2. So this is a vector space. So this is a vector space, meaning that it is basically kind of like Rn. They are basically kind of like Rn. So if you have theory for Rn, that theory will work for this as well because they are basically essentially the same. Okay, and we are also going to call the elements in this set as vectors. So you don't be surprised that from now onwards, we can actually say that 1 plus x is a vector. We can also say that 1 plus x squared is a vectors. We can also say that x squared is a vectors because they basically behave like a vectors. Okay, so now we are taking a steps forward in terms of abstractions. So sometimes people can actually point to a polynomial and say this is a vector. When people say that, they are thinking in terms of vector space. They are thinking in terms of like, oh, those polynomial, I'm just going to view them as the vectors. Okay, all right, so let me show you another example. So this is a set. This is M2 by 2. All right, let me write down the sets builder notations. This is a set of all the elements that looks like this. Okay, so it looks like A, B, C, and D. Okay, and A, B, C, D here, they are just real numbers. So this is again the sets builder notation. Either you write like this or you write like that. So M2 by 2, this is a standard notations, stands for a set of all the 2 by 2 matrices with real entries. And now this is just a set. We can't talk about vector space yet because vector space consists of a set together with the addition operation and scalar multiplications operations, right? So we have to talk about how do you add vectors? How do you add these 2 by 2 matrices? We add it the same way that how we add matrices. So this is how we add matrices. So we define the addition operations like this, okay? And we are going to define the scalar multiplication like this. This is the usual additions and usual scalar multiplications. And again, you can go through all this property and you will see that all that 10 properties is satisfied. So it's a lot of work, but you can look at it and you can actually see that all these things are satisfied. It's not a big surprise. And because of that, this is now behave basically like Rn. They are essentially going to behave like Rn. So everything that we develop, all the theories that we develop for Rns, it actually works for this one also. So we call this vector space, and we again call every element inside the sets as a vector. So we can actually point to 1, 2, 3, 4 and say, hey, this is my vectors. That's completely fine because we are taking the perspective of like, hey, this is basically going to behave like our Rn. So this is another example of a vector space. Okay, let me give you another vector space example. So this one right here, okay, so this is, okay, let me write down the sets builder notation. So this is a set, okay, very fancy notations. This is written in this interval form. Sometimes you can also simply write it like this, okay? And this is a set, consists of all the functions, okay, such that f is a function that take a real numbers and map it to a real numbers. So again, this is the sets builder notations. So you can see the elements in this set is all the functions. Okay, what type of function are you talking about? You're talking about the type of functions that takes a real number and map it to another real number. So for example, sine x, okay, is in this, okay, sine x is in this set, x squared is in this set, okay, and your exponential functions, ex, is in this set, so on and so forth, okay? All right, okay, so 1 over x, however, is not in this set because 1 over x is actually a function that define everywhere except x equal to 0, but we are actually talking about the domain here has to be R. So this is kind of like the stuff that is in this set. So we have a set of all the real value functions, okay, that is defined on this interval R. So now we are looking at the elements that is in this set. We call that f, which is fx, g, which is called gx. And the way we define additions and scalar multiplication is this. So one thing is that when you look at the function sine x, okay, so you look at a function sine x or x squared or ex, this is not in this, so we don't care about this one right here. But all the functions here, we can add them and we can do scalar multiplications. And the way we add two functions is the usual way we're adding it. We're adding it point-wise, which means that you put an x here, we evaluate that x at this function f plus g. The way we evaluate it is to evaluate it at the function f and evaluate at the function g. These are all two just number. You add them up. This is how we add two functions. This is how we scalar multiply functions with a scalar. So this is the usual function additions and scalar multiplications. So what I'm claiming is that, again, you can go through this and you can verify that yourself, that actually this set, okay, this as a set together with the additions, okay, and scalar multiplication defined like this, this again satisfy this 10 axiom. So this again will satisfy this 10 axiom right here. So again, basically, this basically is the same as Rn together with the plus and the scalar multiplication right here. They are basically the same thing. All right, so this is a diagram that kind of indicates what we are talking about. So when you talk about function f, you talk about the whole thing. You talk about function g, you talk about the whole thing. And the way we add it pointwise, which means that for a particular x, this point here and this point here will add up to this. For a particular x, this point here, scalar multiply will add up to this, so on and so forth, okay? So this is nothing really new. This is actually how we define our usual function addition and function scalar multiplication anyway. And you can verify that actually all these properties still satisfy. So we can actually now point to a function sine x and say, this is my vector. This is a vector. Why is it a vector? Because it is an element of the vector space. What vector space are we talking about? We are talking about this vector space. Okay, so this, okay, is a vector space, right? Why is it a vector space? Because it satisfies this 10 axiom. Anything that satisfies these 10 axioms, it will be a vector space, and every element in it will be called a vector. So again, if you have a theory that works for this, it will work for this as well. Okay, now let me ask you a question. So suppose you have a set, okay, V, which is R2, and the additions is the usual additions that we have. You have a vector U, you have a vector V, and U plus V is defined like this. But the scalar multiplication is slightly different now. The scalar multiplication is not the same as the one that we defined. So now the new scalar multiplication is defined this way. If you have a k, multiply u, you multiply the k to the first components of your vector u. Okay, look at this. Multiply the k to the first component. But then you drop this u2. Okay, you drop this u2 and write it as 0. So this is how we define our new scalar multiplication now. So the questions that I have for you is that with this r, okay, with this r, same r as before, with this usual, okay, scalar addition, sorry, the usual additions, but the new scalar multiplications, will this be a vector space? Will this be a vector space? Okay, so the question now is, this sets, even though it's the same, we have the usual addition, but now we change our scalar multiplications to this. Will this be a vector space? That means that whether or not this will satisfy this 10 axiom. Are you sure that will always satisfy all these 10 axiom? If the answer is yes, okay, if this, okay, usual additions and the new scalar multiplication with the sets will still satisfy this 10 axiom, then it will be a vector space. If you can find any of the axiom here that will not be satisfied with these new operations here, then the answer will be no. Okay, so the question is this a vector space, or is it no? Okay, or is it not? All right. I'm going to give you a moment to work on these problems. Then I will come back and we can look at the solution together. All right, welcome back. And I hope you already have your answers. And the correct answer is no. If you go through this list and you will see that, for example, your axiom 10, the last, very last axiom does not hold. In fact, everyone else, every other thing, everything checks out, but axiom 10, because as you can see, if you have 1 times the vector u, the new, okay, scalar multiplication says that this is what you have, right? 1's multiplied to the first element right here, but the second element here will drop to 0. So you get this instead. And obviously that is not your original u. So you will see that axiom 10 fails, which means this set, even though it's the same R2, okay, but with this new operation here, it will not behave like the usual R2 with the usual additions and scalar multiplication. So they are different. They are not the same thing, okay? So this will not be a vector space. So this will not be a vector space. This will not be a vector space. This is an example to indicate, to show you that you can't just say that, hey, R2 is a vector space, okay? When people say R2 is a vector space, it's always with the usual addition and scalar multiplication. When people say R3 is a vector space, it's always with the usual addition and scalar multiplications. But if you change the operations, then you might not get a vector space. And also, this is the example to show you that we are not just simply talking about a set. So a lot of people say R2, R2, R2. That is for convenience. Actually, those are the R2 with the usual addition and scalar multiplication. But you can change how you add and how you scalar multiply, still using the same set. So again, this is just to illustrate and to emphasize that a vector space consists of three things: the set, the addition operations, and the scalar multiplication. And this is an example to show you that even though we are in the very familiar R2, we have a very familiar additions, but your scalar multiplication is different. You will see that in this case, axiom 10 fails to hold. Therefore, it will not be a vector space, okay? It will not be a vector space. All right, let me ask you another questions, okay? So now again, we are in a very familiar space called R3. Again, this is your vectors U in R3. You have a vectors V that is also in R3. And the additions is defined the same way as usual additions. Okay, but again, the scalar multiplication is defined differently. So if you have K, now you have K squared, K squared, K squared instead of the usual K. So the question now is, if you have, again, this set. So this is just a set, okay, with the usual, okay, additions. But again, with the new scalar multiplications, is this a vector space or is it not? So the question is this a vector space? Okay, or is it not? Yes or no, right? Yes, if it's yes, then you have to make sure that it all satisfy this 10 axiom. But if any of this axiom fails to hold, then the answer will be no, okay? All right, I will give you a couple of minutes to work on the problems, and you can pause the video, and when you are ready, you can restart the video and I will come back and we can look at the solution together. All right, welcome back, and I hope you got the answers, and the answers is actually no, okay? So in this case, you can see that axiom 8 fails to hold. So axiom 8 says that if you have this, you should be able to distribute the u into it and get this. So let's do the computation on the left, and then let's do the computation on the right and see whether or not they are the same. So if we have k and m, okay, and I'm changing the scalar here. I didn't call it CD, I call it K and M. So you have K, M right here. So this is a number, right? The number multiply this with the new scalar multiplication. We will have to square them. And that's what we got, okay? So the left-hand side of the computation give you this. The right-hand side of the computations, if you take K and U will give you this. And then if you do M and U will give you this. And then now, if you look at this steps to this steps, okay, so this is vector additions, the usual additions. There's no scalar multiplication now. So this is one vector, add another vectors. So the way you add it is component-wise adding, components-wise adding, component-wise adding, component-wise adding, and you can factor out the U1, U2, and U3, and you will get this. So you will see that this one right here, which is the right-hand side of the equations, this one right here, which is the left-hand side of the equations, they are not the same. So they are not the same. So you can see that axiom 8 failed to hold. You don't really have to show the axiom 8 failed to hold this way. If you want to show something does not hold in general, you can also do it by example. So this is showing it by a particular example. Let's say I take 2 plus 3 with 1, 0, 0. So 2 plus 3 is 5. So the way we multiply this is to square them. So I have 25. But if I do 2 of this and 3 of this, that will be 4 of this and then 9 of this because of the square. And then by adding it up, you get, I added wrongly. So why do I write 11? So, sorry. So if you write this thing up, you will get 13. But anyway, these two are different. So in general, you will see that this is different. Okay, so this axiom 8 failed to hold. You can show it like this, which is easier, I think, or you can actually show it like this. So if you think something does not hold, then you can actually show it by an example, okay? So using some special numbers here, it doesn't have to be this number. You can come up with some other numbers, and now you will see that this R3 together with the usual additions, but the new scalar multiplications, this is essentially different from the usual 3 with the usual addition and the usual scalar multiplication. So this is not a vector space. So this is not a vector space. It would not behave like the usual R3. So the moral of the story is that if the set is the same, doesn't mean it's a vector space. We say this is a vector space because we are lazy to indicate that we are actually talking about this with the usual addition and scalar multiplications. You can actually have R3, but the different operations defined on it. And with these new operations, you don't have that 10 axioms satisfied, then this basically does not behave like the usual vectors that we know. Okay? All right. So this is basically what you need to know on vector spaces. Okay. All right, this concludes our discussions on section 4.1, which is real vector spaces. And the next video, we are going to study another concept called vector subspace. So what is a subspace? So basically, subspace is a subset of a vector space, which itself, together with the same operations that we have, also is a vector space. So this is going to be something that is pretty interesting. We're going to look at a lot of different examples and to figure out what is a vector subspace, and we're going to see you there. All right, see you then. Bye.